Hi everyone, welcome back from break. And hope you had a good time, hope you had a good break. I had a great break. I went to England, went to London, Cambridge. My son got married. Yeah. It was it. Oh, thank you. I appreciate it. It was an amazing time. And get this, the two families, the groom and the bride's family, spent a week together in a bed and breakfast, and we rented out the whole bed and breakfast, and we all got along. It was sort of amazing. I don't know how that happened, but I think it was a big relief, yeah. So I'm feeling pretty wonderful about that, but my mind is not on statistics. So I'm probably in the same boat as you guys are in right now after a week's vacation. You know, I'm just really, my mind isn't, but let's try to focus and get back, because this is one of the most important chapters for the whole semester, okay? So, now, what's all that sound? Is that us? Whoa, that was us. I thought it was out in the hallway. Okay, quiet now, we've got to focus. All right, so do you remember where we left off? We were talking about these probability histograms, and we looked at this amazing fact called the central limit theorem. And what it said is, we turned the page. This isn't my book. Oh, this is kind of cool. It's somebody else's book here. But what it says is that regardless of the contents of this box, remember we're looking at numbers generated by a chance process. We're talking about the statistics for chance numbers, gambling games, and later on we're going to talk about sampling. Okay, so regardless of the contents of the original box, with a large enough number of draws, like let's say I drew from this box over and over and over again, the histogram for the sum, like if I drew 100 times from this box, the most I could get if I was taking the sum of the 100 draws would be 300. The least I could get would be 100. I'd expect 200. But the amazing thing is that the histogram for the likelihoods of one and everything in between, you know, from 1 to 3, the histogram would look just like the normal curve. And same for this one, but this box is more abnormal to begin with, so it would take longer for it to reach normality. I'm afraid to switch to the document camera to show you what I mean, but I think a visual is helpful here. I'm afraid, because I heard something weird might happen, but let's see what happens, okay? The normal approximation for chance numbers. We've already used this normal approximation a lot. Z-scores, you've already used it a whole lot. Remember? But what did we use it for? We used it not for chance numbers, but just for a given list of numbers, a known list of numbers, or a known data set. Like we used it for what? We could use it for questions, variables like, what's your height? Or what's your weight? You know, ones that follow the normal curve. But we couldn't use it for anything else, like for how many pairs of shoes you had. That was very skewed to the right. Or for our exam scores, which are very skewed to the left. We couldn't use it for many data sets. We could only use it for those that followed the normal curve. Well, the most amazing thing about the central limit theorem is that it enables us to use the normal approximation no matter what the original data looks like. If what we're doing is a chance process, if we're summing the numbers, the tickets drawn at random from a box, or we're looking at the average of the numbers, or the percentage of ones in the data set. And that's that's going to be extraordinarily useful in all our inferential statistics, including, we're going to start with gambling, and then we're going to apply it to sampling and analyzing, hypothesis testing, just everything pretty much. Okay, now, so it means that instead of drawing these actual histograms that take a huge amount of time, those histograms that you saw that take a lot of time, what can we do? We can substitute the normal curve. And all we need to know to figure the chances of anything within a given interval is the expected value and the standard error, which is pretty much the same as what we did before for what? For numbers, look, you can use the normal curve to calculate the chance the sum of a number of draws made at random with replacement from a box falls in a given range. And we convert it to a z-score. So this is what we do using the expected value and the standard error. So this right here is for chance numbers, okay? For any chance process. Whereas what did we have before? We had, do you remember? Value minus the average divided by what? Not the standard error, but the standard deviation. And we did this for what? Just a given list of numbers, not for a chance process. Okay, so we'll just say for a list of numbers, an actual data set. All right, so here's how it can be so useful. Let's check it out. It says here, in 100 coin tosses, if you tossed a coin 100 times, what's the chance of getting less than 45 heads? Less than 45 heads. Well, we could figure out the exact probability histograms, didn't we do that? Check it out, we did it for, what? Well, one toss looks like this. You could either get 0 or 1 head. And then after 2 tosses, here were the probabilities. We could either give 2 heads, 0 and 1. After 2 tosses, we could get, after 3 tosses, there's 8 possibilities, 2 to the third, and here they all are, and here's our histogram for it. And after 4 tosses, there's 16 possibilities, and we drew them all out. This is on page 177, and you can see it already looks normal. And after 4 tosses, you'd expect half heads too. So, do you know guess how many possibilities there'd be for 100 tosses? It would be 2 to the 100th, which is an extraordinarily large number. We looked at that last time. Remember, I told you if we tried to write down all the possibilities, 2 to the 100th, we said that that's equal to 1.27 times 10 to the 30th. Didn't we talk about this last time? And I told you that if you wrote 100, if you wrote the possibilities down on sheets of paper, and you wrote 100 possibilities on one sheet of paper, and then the next you wrote 100, and the next, there'd be what? 1.27 times 10 to the 28th sheets of paper? And it would reach, that's a big number, 10 to the 28th. And even though a sheet of paper is really, really thin, it's probably like, I don't know, what, 0.003 inches or point something like that. If you had 100 of them stacked, it would reach to the farthest known star. That's what we talked about. So it's a lot of possibilities. We couldn't really do those histograms the way we did the ones for 4 tosses, but we can use the normal curve, for sure. And so we can figure the chance of getting less than 45 heads just using the normal curve. Hey, what do you intuitively think it is? What do you think the answer to this question is? Write it down. I'm just curious. Just write it down for you. What do you think? In 100 tosses, what's the chance of getting less than 45 heads? What does your intuition tell you? Let's just think about it for a moment. Okay? So 100 tosses, we're going to translate to a z-score, but let's just think. In 100 tosses, you'd expect right in the middle how many heads? You could get as many as 100 way, way, way out. You could get 0. That's very, very unlikely. But what would you expect right in the middle? How many heads? 50. All right. So the question's asking us where to place 45 on this normal curve. Is it going to be really unusual? Is it going to be really close to 50? That's what the question's asking us. We're going to translate 50 into a z-score. That's what we're going to do. But intuitively, do you think 45 would be... This actually, never ever crosses, it never gets negative. There's never going to be a negative chance. And this goes all the way to 0 heads in this direction, but it's such a tiny chance. And it goes all the way to how many heads? What's the highest you could get? It'd be so unlikely, but flipping a fair coin, theoretically, you could get what? If you flip it 100 times, what's the most heads you could get? 100. So theoretically, this curve goes way out to that, just goes on forever in either direction. Okay, goes on for a long, long time. Now, we expect to get 50. So you can just write down for your own, just write down some number, what you think it would be, and let's figure it out exactly now. Where do we put 45 on here? Is it going to be pretty likely? Is it going to be very unlikely? Where's it going to be? That's what we're going to try to do. Okay? So, we start by translating it into a box model. So, draw a box model for tossing a fair coin. So, what should we put in the box? Remember, the key is don't think about it for 100 draws, even though that's what we're doing. Think about it just for a single toss. It's so much easier to draw the box model for a single toss. So on a single toss, you could either get 0 heads, which is a tail, 0 heads, or 1 head with equal likelihood. So that is our box model. All right, now find the expected value and the standard error for the sum of 100 draws. Well, the expected value for the sum, it's going to be 50. And you really wouldn't have to do any more work. On an exam, if you just used your intuition and said 50, you will get it right because you really don't need a formula. But if you wanted to use a formula, you remember that the sum is the only one that even has a formula. The average and the percent is a no-brainer. It's the same as the sum does have this formula, n times the average of the box. And we better get 50. And n is the number of draws. So right here is n. That's 100. And the average of the box is obviously what? Obviously a half. Because you have one of these, which is 0, one of these, and one of those. So we have 1 0 and 1 1 over 2 tickets. And that's a half, but you knew that already. Times a half, and of course we get 50. So that's the expected value of the sum, but we knew that to begin with. We didn't really have to do any work. The interesting thing is we know that the expected value is 50. We know 45 is 5 less. We just don't know how many standard errors that is. That's what we got to figure out, how many standard errors. So the standard error for this sum, and that's the one that's not intuitive. You can't just pop that off the top of your, just blurt that out. And I don't know anybody who intuitively thinks statistically from the get-go. I mean, they might have, certainly statisticians after a long time, a lot of practice, start to think statistically, but I don't know anybody who started off hardwired to think statistically and know that the standard error is the square root of n. Whereas everybody knows this, people wouldn't have known the square root of n times the standard deviation. Who would even think of a standard deviation intuitively? Or the square root. So that's what it is, the standard deviation of the box. That's that important square root law, where standard error is the same, is basically a standard deviation for a chance process. That's how you remember that. But the more draws, the variability changes with the number of draws. And for the sum, it's multiplied by the square root of n. All right, so we have the square root of n is 100 draws times the standard deviation of the box. You probably remembered that for a 0-1 box, the standard deviation and the average are both a half. Why? Well, because the average is a half and we only have 2 deviations. 1 deviates, 0 is a half below a half, and 1 is a half above a half. So the only 2 deviations you have are a half and a half. So your typical deviation has to be a half, right? You only have 2 tickets and they both deviate by a half. So you have to have a standard deviation of a half, but we know how to figure it out another way, and that's do the shortcut, we look at the 2 numbers on the tickets, and we say, okay, that's 1 minus 0, the absolute value, times the square root of, and we have 2 tickets total, and we say the fraction of the tickets that have this, that have 0 marked on it, and 1 out of the 2 tickets have 0 marked on it, times the fraction of the tickets that have 1 marked on it, which is 1/2. So we have 1 minus, 1 times the square root of a quarter, which is 1/2. Okay, so we've got those. So we have the square root of 100, which is 10, times 1/2. So our standard error is 5. So now we'll see, I bet you can see where 45 is going to be placed. Here's a z-score of 0. And if we go down 5 to 45, we're only going down 1 standard error. You can see where we're going to end up. Okay, so we're just going to use the formula, though, to see that we're going to end up right there. So z equals, remember, the value, which is 45, minus, not the average, but the expected value over a standard error. So that's 45. Now, which expected value should I be talking about here? What am I talking about? Am I talking about sums, averages, or percents? Sums. So that's the standard errors we're going to be using. So 45 heads minus 50. There's the 5 heads we're talking about. 45 is 5 below 50. That's what that numerator tells us. But 5 below, how do you know where to place 5 below? You don't until you know what that is. How many standard errors is that? This will be 1 standard error. This will be 2. Well, the standard error is 5. So that's why we have 1 below, right? So this is where 45 is. It's just 1 standard error, which is -1. And that's where 50 would be. 55. This is 50. 55 would be here. All right. So now the area that we want is where? Y'all know it's what? Below. Isn't that the question? What did the question ask? Below 45, right? Getting less than 45. Isn't that what it said? Yeah, less than 45. So we want to shade in this area, less than 45. And what is that area? Do you remember between 1 and -1 on the normal curve is what? Shout it out so I know you know it. 68%. So this is 32 together. So this has got to be 16%. And that is our answer. How many people were pretty close to that when they did it intuitively, when you wrote down? Were you greater than that? Raise your hand if you thought it was greater than that, the possibility. How many people thought it was less than that? So more people thought it was greater than, although most people didn't vote. Okay, maybe you didn't have an intuition about it. All right, let's turn the page. Now, we're going to do the same thing with percents. We can do this with percents, with averages, and with sums. They're all basically the same idea. All right, so again, what's the question asked? In 100 coin tosses, what's the chance of getting between 40 and 60% heads? So intuitively, well, first of all, our box model is going to be the same. You make it for a single draw, and you can either get 1 head or 0 heads, right? Find the expected value and the standard error for the percent of heads. Well, what's the expected value for the percent of heads? I mean, there's a 50-50 chance of getting a head or a tail. So what's your expected value going to be for the percent of heads you get no matter how many draws there are? It's a fair coin. So what percent, here, this is all I'm asking, percent. Here, we're going to change it to a z-score. But right in the middle, you could get 100% heads, you could get 0% heads, but that is highly unlikely. It's a fair coin, so what would you expect to get? What percent? 50. Duh. Please don't get that wrong on an exam. That would make me feel like I taught you less than you knew when you were about 8 years old, when you probably already would have known the answer to that. No one should ever get that wrong. Okay? It's obviously 50%. And the reason you can, in general, you can think of it as this. You can think, okay, we have 1 and 0, so that's 50-50, 50%, 50%. So obviously, the expected value for the percent is the same as 50%, and the expected value for the percent of anything is going to be equal to the percent of, well, if it's a percent problem, you're looking usually at 1s and 0s. You classify it into either is that category or it isn't. So it's just the percent of 1s in the box. So if it was, oh, I don't know, tossing a die, or let's say it was just an unfair coin, you know, and they had 20% likelihood or 45% likelihood, then it would be 45%. Okay, so we've got that. So that doesn't help us at all, because what are we trying to figure out? 40 and 60. Okay, so what's the chance you're going to get between 40 and 60% heads? Where's that going to be? You might just want to think intuitively what you feel where it would be. What would be the chance in 100 coin tosses that you'd get between 40 to 60? Do you think it's overwhelmingly likely? Do you think it's about, where do you think it is on here, between 40 and 60? It's really hard for people to have, most people don't have a real good intuitive sense of that. You can write down just for your own what you think the answer is going to be, and then we'll figure it out. Okay. Where do you think? What do you think? This is the question we're asking. What's the chance of getting between 40 to 60% heads? Do you think it's over like 99%, 90%, 80%? What do you think it is? Okay, well, maybe only 50%. So what do we have to do? We have to figure out the standard error. We'd expect to get 50%, give or take what? And that is, well, standard error, right away I'd write down standard deviation. It's like a standard deviation. Now the question is, are you going to multiply or divide by the square root of n? Which do you think? For a percentage. Do you think your error is going to grow the more time you use it, or shrink? What do you want me to do? Divide or yell it out? Divide. Okay, so you know the answer. All right, so that's the square root of n, and that's not a percent yet. That's just a decimal. To change it to a percent, I have to multiply it by 100, and that changes it to a percent. All right, so it's going to be divided by the square root of, what's n? 100 times 100%. But now we have to put the standard deviation. Well, it's just the standard deviation of this box. We already know it. We just figured it out last time. But if you wanted to figure it out alternatively using these numbers instead of, what did we do last time? We had 1 and 1, so we did it like this. Well, we can do exactly the same thing with, we can say 50%, 50%. Okay, it's exactly the same thing. So we will, and we'll say the standard deviation, the absolute value of 1 minus 1, times the fraction of the tickets, the percent says 0.5, times 0.5. Don't write it as 50 times 50. This has to sum to 1. That's the fraction. Okay, so it's the square root of 0.25, and we know that's a half, or 0.5. All right, so we'll put that right in there. That's 0.5 divided by 10 times 100 is 5%. That looks like the same thing we got with the sum. It is the same thing, just because we're taking it out of 100. Percent means out of 100. If it was any other number, it wouldn't be the same. You'd get a different number here. All right, now we're going to convert. Where are we going to put, let's take these endpoints to z-scores. So let's do that. So, whoops, what do we want to do first? For both of them, we want to say z is equal to, this is our value, and this is our value, minus some expected value over some standard error. And we're talking about percents, not sum, so these are going to be percents. So for 45, we'll do it for 40, 40% minus 50%. We know our numerator is negative 10. Yeah, we're 10%, but where do we place it? Well, we don't know until we know the standard error for the percent, which is 5%. So we see that it's -2. So that's where we put 40%, way down here in 100 coin tosses. It's really unlikely to get less than 40%. That's where it is. I don't know if you thought that intuitively, but it's way less than 40% is that little area. Less than 40 heads out of 100. That's, okay. And now we have to do this one. That's this. Now we have to do the 60% minus 50%. It's symmetrical over 5%. So we're going to get what? Positive 10 over 5. So that is a z-score of 2. The percents cancel, and it's a z-score of 2. This one's 2. So it's way up here. This is 0, 50%, z-score of 0. And now we go all the way up to here, and that corresponds to 60% and a z-score of 2. So the chance of getting in that interval is overwhelmingly likely. It's all that, which we know is about what? 95%, between 2 and -2 on the normal curve. Is that what people thought intuitively? Raise your hand if you really sort of estimated that. Didn't most people think it was, I intuitively would think it was a smaller. Did anybody estimate it smaller? That's what I would intuitively think. Okay. Now we're going to revisit an old problem. Oh, whoops. Okay, so we're revisiting this old problem we did. I just want to show you, this was a problem we did where we already figured out everything, the expected values and the standard errors. We just didn't figure out chances. We didn't use the normal curve. So if you look back at chapter 14, example 2, let's see, we already did this. Example 2, chapter 14, where was that? Example 2, oh, I didn't do it in this book. Did I? Or did I? Maybe I did. Ah, this book's empty. All right, we'll have to do it again. All right, so let's start doing it. You'd expect the sum, so we're drawing from this box. Let's make a box here. All right? And let's do the average of the box. What's the average of this box? What's it look like? What is the average? What is that? You probably have it in your notes. You can turn back. The average is what? Let's add it up. Why do I want the average? Because it says you'd expect the sum of the 36 straws to be what? Well, we're not going to get all 36 zeros, and we're not going to get all 36 eights, so it's going to be 36. The expected value for the sum is n, which is 36, times the average of the box. So that's 36 times, we just have to figure out this average of this box, which isn't hard. 8 plus 2 is 10 plus 2 more is 12, divided by 1, 2, 3, 4. So that's just 3. Okay? So that is what? 18, right? 108. Right? Yeah. Okay, but give or take what? It's a chance process. It's going to vary. What's the standard error for the sum? That's what we want to put right in here. The standard error for the sum. So what is the standard error for the sum? Now you write down a standard deviation, and the question is, are you going to multiply or divide? You're going to multiply by the square root of n. You can do it either way, square root of n. So that's the square root of 36, which is 6 times. Oh, does anybody remember what it is, or should we have to do it from? Do we have to do it from scratch? Want to look? Do you want me to do it? All right, we'll do it. All right, what are we doing? We subtract the average So 0 minus 3, we get a negative 3. Another deviation is, what's that? 2 minus 3. That's another one. We're just getting our 4 deviations. 2 minus, what's our last deviation? Hello, what's our last deviation? 5, thank you. Oh, you're back. Did you have a good break? Good. Okay. All right, so now what do? We have to square all these. The root mean square. Square, 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 square. And then we have to take the mean, the average of them all, which is plus, 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 divided by 1, 2, 3, 4. And then we're finally going to take their square root. So that is going to be our answer. 25, 26, 27, plus 9 is 36. Square root of 9 is what? 36? 3. So there's our standard deviation. Where can I put it? So this equals 3. All right, times 3. So we have 6 times 3, which is 18. All right, we're good. So what does this mean? What's the chance that some of the draws of the 36 would be greater than 120? So what do we know? As a z-score, right in the middle is 0. But as an actual sum, right in the middle is what? 108, the expected value. 108. That's what, and we want to know what? What's the question asked? 120, that's our value. That's 12 above. All right, where do we place that? We have no clue, right? 12 above, where is that going to be? And that's why we need statistics. We've got to say z equals our value, which is 120, minus our expected value over our standard error. And we're talking about sums. Sum, that's what that says. That scribble, sum. All right, so that is 120 minus 108. That's where our 12 is. That we have no clue where to place that 12. It's 12 above. Until we divide by 18. So that is what? 2/3. So it's not even, it's just 2/3 of the way up to 1. Whoa, that's not really that unusual. So we have to get between 0.67 and negative 0.67. And what we want is the chance that it would be greater. So this is our chance right there. That's 0.67 corresponds to 120 is right there. All right, so we look up 0.67, and what do we get? 0.67 is, 50. Let's do 50. 50, right in the middle. 50% here. So this this one has to be what? They have to add up to 100, so this one has to be 25. Okay, that's our answer, 25%. Where should we put that? What's the chance? So our answer is 25%. Cool. Now we're just going to do the same thing. This was for sum, okay? We're going to do average, and then we're going to do what? Percent. But percent of what? We're going to look at percent of 2's. Okay, so let's just do sum and average first, then we'll have to do something, change the box to 0's and 1's to do percent of 2's. All right, so you'd expect the average of the 36 straws to be what? Well, the average of the box is 3. So why would you expect it, no matter how many draws you take out of here? The highest the average could be would be 8. The lowest it would be 0, the average. If you got all 0's, your average would be 0. If you got all 8's, your average would be 8. But on the average, you'd expect to get 3. So what would you expect, no matter how many draws? What do you expect the average to be? The average of the box is 3. You'd expect the average of your draws to be what? 3. No brainer. I don't want anybody to get that wrong. On an exam, it would be 3. Why would you expect it to be any higher? The most it could be is 8, and that would only happen if you got all 8s. The lowest it could be would be 0, and that would only happen if you got all 0s. The average of the box is 3. So we expect the average of our draws. If this was 360, it would get even closer to 3. I mean, even more likely to be closer to 3. Okay, so let's write that down. The expected value, and I want you to just, there's no formula for it. It's just obviously common sense, is just equal to the average of the box. And so all we're saying is, as a z-score, we expect 0 down here, but as an average, when we're talking about averages, we expect this to be 3 right there. And the question is what? What's the chance that our average of the draws will be less than 4? Well, the chance that it's got to be a pretty big chance, certainly greater than 50%. All right, give or take about what? That's the standard error for the average. That's what I have to put in right here. So that's going to be the standard error of the average. And right away, standard error SD. Your only question is multiplying or dividing for the average, you divide by the square root of n. So standard deviation, we just figured it out. It's right there, 3, right? So that's 3, happens to be the same as our average. Over the square root of, what do I put here, 100? Are there 100 draws? No. This is n. There are 36 draws. So it's 3 over 6, which is 0.5. That's what goes there. All right, now we can answer the question. Where to place 4 on here? Its 0.5 is 1, and another 0.5. So this would be 3.5, and that's where 4 is going to go, way up there. So the chance is going to be, what? You can do that in your head, but we'll do it out here. So z is equal to our value minus the expected value over the standard error, and we're talking about averages here. So we have 4 is our value, minus 3, it's 1 above. But 1 above is how many standard errors? 2, because the standard error is a half. So it's 2. This would take you to 3.5, and this takes you to 4. That's what that is. All right, so that is overwhelmingly likely, because we know, and what did I write here? You should all be saying, what is she doing? This took me to 3.5, but 0.5 is not 0.5 a standard error. 0.5 is 1 standard error. You go over 0.5, and that's 1 standard error. And you go over another 0.5, and that's 2 standard errors. So I go over 0.5, I get to 3.5, go over another. Sorry. So it's 2 standard errors. And between 2 and negative 2 is 95%, and this is 2.5%. These two are 5% together, 2.5%. Here we go. So our answer is 95, oh, it didn't look pretty. 95 plus 2.5. That's our answer, 97.5%. Does that make sense to everybody? Does it? None of it makes sense. Okay. 95%. I should have made this bigger. That's 95 and 2.5. All right, now, so what have we done so far? We figured out for sum and average. All right? Now we're going to look at the chance that we're going to do a percent problem here. And what we're going to be looking at is what? The percent of 2s. We could look at the percent of 8s, but the question asks the percent of 2s in 36 straws. Well, you know 50% of the box is 2s. So what would you expect? I don't care how many draws. What percent of your draws would you expect? Even if you have, no matter how many draws you have, let's say you have 50 draws, 100 draws, what percent of them would you expect to be 2s? 50%. Even if you have an odd number, even if you had an odd number, you'd still expect 50% because the expected value doesn't have to be something that you'd actually get. All right, now that's 50%. We know it. So in other words, we already know that the percent of 2s, what did I do? Why? It's because the controls are they're very sensitive and they're really close to my hand. So now I just got to figure out what to do here. Okay. Good, we're back. Okay. So you'd expect the percent of 2s to be 50%, and let's write that down. The expected value for the percent of what? Of 2s. And I don't care how many draws, is just going to be equal to the percent of 2s that are inside the box. And that's 50%. All right? We haven't answered this question yet. This right here is going to be the standard error for the percent. That's what we're going to put in here. To find the standard error of the percent. How are we going to do that? We want to put it in there, the standard error, but how are we going to do it? The percent of 2s in the box. Well, the percent of 2s, if you get a 2, you're going to count it as, that's like counting up the number of 2s. If you get a 2, you're going to count it as 1 2. And if you don't get a 2, you're going to count it as 0 2. So we have to change this. We're only going to count it if we get a 2, so we have to change it to a box that just has 0s and 1s. So if we get a 2, like here, we'll count it as a 2, but if we get anything else, we'll count it as 0s. So do you see how it's just going to be 0? This one's going to change to 1 2, 1 2, and what's our last one? It's not 8, but what is it? How many 2s is it? 0. We're just interested in the percent of 2s. Whether you get a 2, you count it as 1. All right, so that's it. Now, because taking the percent, if I want to know the percent of girls in this class, if I came across a girl, I'd say I count her as 1 girl. 1 girl. Come across a boy, I count them as 0 girls. And I count up everybody, divide by how many people there are, and then multiply by 100 to get the percent. All right. So we're just doing, you always do that. With a percent, you're just interested in 0, 1 box. So the standard error for the percent is going to be always equal to the standard deviation, let's write, of a 0, 1 box. You're not going to use the standard deviation of that box. You can't. It's a whole different standard deviation. We're only interested in whether it's a 2 or not. Divided by the square root of n. So far, that would give me the fraction. But I have to multiply by 100 to get the percent. All right, you know this already, don't you? The standard deviation of this box, it's half 0s and half 1s. So what's the standard deviation? 1/2. Do I have to do it? I mean, you could, if you wanted to do it, you could say, okay, absolute value of 1 minus 0 times, how many tickets are in the box? 4. 2, half times a half. You can think of 0.5 times 0.5, square root of 0.25. So this is 0.5. That's our standard deviation. I'm glad you knew it, most of you. So that's 0.5 divided by the square root of, now do you remember what n is? 36. So it's 0.5 divided by 6 times 100. So that's the standard error. 5/6. All right, so that's what? I'm going to put it right here. That's 8.3%, right? 3%. Yeah. So that's our answer. 50%, give or take 8.3% right there. That's the standard error. Okay, question so far. By the way, what if it was the percent of 8s in the box? Then this 8, it would be a box that had just 1/4 of the box. 25% of the box would be 8s, would be 0s. Oh, 25% of the box would be 1s for an 8. And then the standard error would be smaller. We'd have a 1, 0.25 times, square root of 0.25 times the square root of 0.75. All right, what's the chance that the percent of 2s would be more than 60%? Well, we expect 50% 2s, correct? Which is a z-score of 0. And would be more than 60%? So 10%, 10 more is going to be where on here? 60% is going to correspond to where? Well, we just do z is going to be equal to, this is our value right there, 60% minus 50%. That's our 10%. We just want to know where to place that 10%. How many standard errors is it? Well, you don't know until you divide by the standard error, which was 8.3%. So it's 10 divided by 8.3%. So it's just a little over 1 is our z-score. Correct? A little over 1. It's about 1.2. So that's where we're going to place 1.2. That's where we're going to place 60%. And what's the question ask? More than 60%. So it's going to be this area right there. Okay? So between 1.2 and negative 1.2, we have to look that up, would be 77% in the middle, and you know where to go from there. 77%, so that's 23% divided by 2 is 11.5% on each tail. That's our answer. Questions on that? All right, let's just do one more page, and we're just going to figure out some, the odds of winning in roulette, okay? Winning anything in roulette. So let's look at that in 2 different games. If you bet on red, or if you bet on, what is it, the same question? You play roulette 100 times betting $1 on red. What's the chance you win more than $1? You bet 900 times. Okay. All right, let's do this. Well, the more you play, the less likely you are to win. So do you remember how the roulette game looks? What do we have? We have 8, if you bet $1 on red, we have 18 reds, just to refresh your memory. We have 18 blacks, but then we have these 2 greens. So here's the box model. You either win or you lose. There's nothing else that can happen on a single play. You either win $1, are we betting $1? Yeah. We either win $1 or you lose $1. This pays even money. Okay? The odds are, it's just pays, you get $1 if you win, and you lose $1 otherwise. Okay? I better write that down. If it lands on red, and I would on an exam, of course, I don't expect you to know the game. If it lands on red, you win $1, because you bet $1. If you bet $2, you'd win $2. If it lands on the other 20 slots, otherwise, you lose $1. Okay, that's how the game goes. So here's losing $1, 18 reds and 20 of those, 20 ways to lose. That's -1 and that's +1. All right, so now what do we have to do? What do we want to figure out? We're always going to have to figure out the average and the standard deviation of the box, so we might as well start there. What's the average of the box? The average of the box is, you have 18 ones plus 20 negative ones. That's 18 minus -2 divided by 38 tickets. Okay, so that's our average of the box, and that's equal to negative about a nickel. So just do it to 4. Okay, that's what it is. It's negative a nickel. And what's the standard deviation of the box? Well, now this one we really have to do out. And remember, we take the absolute value of the difference of the two tickets. So it's 1 minus -1. They're spread out by 2. They're spread out, they're 2 apart. So that's a 2 coefficient in front, coefficient of 2 in front. The more they're spread out, the more your standard error, times the square root of, there's 38 tickets. And how many of them have one of the numbers on them? 18. And how many have the other? 20. Make sure they sum to 1. So that's 2. This is almost a half. 0.5, it's almost a half. So we'll say times a half. And so this is right here. The standard deviation is $1. Okay, now what do we want to figure out? We want to figure the chance of, what does it say? The chance you win more than $1. Okay, so this is going to be in z-scores. We know 0 is right in the middle. And this is going to be in dollars. It's going to be some negative number right here, because you're going to expect to lose. It's going to be some negative number here in dollars. All right, that's a dollar sign. All right, now what's it going to be equal to here? That's the expected value for the sum is going to go right here. So we say the expected value for the sum is n times the average, and n is what? 100 times negative a nickel. So that's negative $5, about 26 cents. All right. An example where the expected value isn't something you can ever get. You're not going to get change ever in a roulette game because you either win $1 or lose $1. All right, now that's your expected value. And what's the question ask? Oh, when do you start winning? Where's 1 going to be? Where's it going to be when you start winning? You'd have to go up. Where's that going to be? Okay? So what do we have to do? We have to get the standard error for the sum, which is the square root of n times the standard deviation of the box. So that's the square root of 100 times what? This is an easy one, times $1. So that's $10 right there. These are dollars, by the way. Okay, so that's $10. All right, so now what do we want to do? We want to get a z-score. We know that when you start winning, it's going to be, if we added 526, we'd get up to 526, we'd get up to breaking even, and then we want $1 more, so 626. We want to know when we're going to start winning. Where is that? Where's that going to be? Where should I put it? It's going to be my z-score. My z is the value minus the expected value, it's sum, over the standard error for sum. So that's going to be equal to, I want to know when I start winning it's $1, minus the expected value is what? negative what? 526, it's right here, divided by the standard error. I'm going to get rid of this so it doesn't confuse you. It's a z-score down there. Divided by what? Divided by the standard error for the sum, which is right here. This is the expected value, negative $5.26. All right, divided by $10. And that's a dollar sign. I don't even know where to put it. All right, so we have $6.26 positive, because we're this side, divided by $10. So that is, the dollar signs cancel out, and we get a z-score of what? 0.626. That's our z-score. So, our chance of winning is going to be pretty, not too low. So it's going to be right here. That's where we get $1. That's 0.626. And what is that chance? Well, you just have to look that up in the back of the book. 0.626. And 0.626, it looks like 0.626, sort of halfway in between there. 46 and a half, we'll just say 46. 46%, we'll say, we'll round. Between. It's just an approximation. I hope I didn't mislead you by doing this exact number here. All right, so what did I say, 46%? All right, and what do we want to know? We want to know coming out ahead, more a dollar. We're doing an approximation, so I'm not saying $1 or more. I'm not really, it doesn't really matter if I say $1 or more than $1, because it's just such a small amount there. All right, so this right here is 54% for the two tails, so this has to be half of that, which is 27%, so that's our answer. Now, if you play 900 times, do you think your chance of winning is going to get bigger or smaller? Do you think if you keep playing more and more, your chance of winning is going to get bigger or smaller? Smaller. This is roulette. This is a gambling game where the expected value is negative. The average of the box is negative. It's going to get smaller. How much smaller? Let's see. Well, we have the same box, so we don't have to do as much work here. We have the same box. So the only thing that changes, just a different what? N. Just a different N. N is equal to 900 now, not 100. So the only thing that's going to change is these numbers right here. Everything else is going to remain the same. So let's see what we'd expect. So our expected value for the sum, instead of saying 100, it's going to be 900 times, here I have more room, I'm going to write it better. This is what I wanted to do. Put the negative 0.0526. So that's going to be what? Negative, it's going to be right here, $47. $47, I wrote this down, and 34 cents. Okay? So that's what we expect to lose. We expect to lose more because we're playing more. But how far do we have to get? How many standard errors before we start winning? This is our Z, and this is our dollars. So now our standard error for this sum, instead of square root of 100, we're just doing this. Instead of square root of 100, we have the square root of 900 times $1. So that's going to be $30. So that's these two numbers, all right? So now, we're going to replace what we had before with that and that. So I'll write it right here. So Z is going to be equal to what? Our value is still $1 minus, so it's $1 minus the expected value, it's going to be 48.34 on top, minus negative 47.34 over what? What's our standard error? 30. So that is 40, did I say 46? I meant to say 48.34 over 30. And that is what? About, no, I didn't write it down. Did I not bring a calculator? Hey, could somebody, oh yeah, I did. Okay, sorry about that. 48.34 divided by what? 30, oh, I should have been able to do this in my head, sorry. Okay, I got it. 1.61. 1.61 is our z-score. So that's right here. 1.61. That's where a dollar kicks in. See how it's a smaller area? Your chances go down. Don't keep playing this game because you're going to more likely to lose, less likely to win. So between 1.61 and negative 1.61, we've got what? 1.61 and negative 1.61, we have about 89.2%. All right, so what does that leave us on either side? 10.8. So this right here is 5.4%. Our chances went way down from 27 to 5.4. Now let's look at the next page for just a moment and look what it says. What is the chance of getting exactly 50 heads? Exactly. Well, I just want to show you, I'm not going to do this problem, I'm just going to give you a brief overview of it. Exactly 50. You know, in 100 coin tosses, 50 is in the middle. But if you've been doing it the way we've been doing it without assigning any area, how can you even do that problem? You have to assign a little smidgen of an area. So the way you would do a problem like this, exactly 50, is you'd make what's called the continuity correction, and you'd figure between 49.5 and 50.5. You translate each of those into z-scores, all right? So you know you'd go 49.5 minus 50 over the standard error, which is 100, and you do the same thing here. Over the standard error, which is, excuse me, what, 5, sorry. And you do the same thing here. But we're not gonna do this problem, so let's skip this. I just wanted to show you how you would do this. You'd make a tiny, tiny little sliver here. And this would be 49.5 if you ever come across a problem like this, and this would be 50.5. All right, but it's such a technical detail and you have enough to do, so let's just skip this. It's just a technical refinement. So we're gonna skip this for the exam, everything. I just wanted to show you that. I'll work it out and post it online if you're interested. All right, so you have homework due Wednesday. See you Thursday.